The second part of this topic, we will discuss another innovative passive metallic yielding damper, known as self-centering box slit damper. Slit dampers are one of the oldest and widely used seismic dissipation technique used in the field of earthquake engineering when it comes to retrofit the existing or design a new structure with dampers. The main advantage of the slit dampers is that they are easy to design, manufacture, and there is no problem as such related to the material because mostly the material is different types of steel. The main advantages of slit damper is also that it exhibits the stable hysteresis loops after it yields, and but the main concern is that after yielding, the post-yield stiffness and strength of the damping device reduces significantly and it cannot come back to its original position. In order to solve these problems, we apply disc springs to provide the recentering and enhance the post-yield stiffness of the slit damper. This slide shows the different component of the box slit damper. 4 slit dampers are cut into the outer steel section and then it is combined with the inner steel section. One end of the slit damper is connected or welded to the inner section. 2 stacks of disc springs are pre-stressed and then they are installed into the damper. The relative movement of the section activates the damper and dissipates the earthquake or lateral induced forces. The overall mechanism of the damper is shown in this figure. Either in tension or compression, one of the disc spring is compressing. The damper starts to activate and dissipate energy when the external force reaches the pre-stress force of the disc springs. Once the slit damper yields, this starts to dissipate the energy. To achieve this self-centering, the pre-stress force should be greater than the yield strength of the damper, as we can see in this figure. This figure shows the layout of the disc springs to achieve the desired force, restoring force, or the displacement of the damper. These are the different phases of the box slit damper specimen. Outer section with the slit dampers, inner section installed with the disc springs, pre-stressed disc springs, and then the complete damper after welding of the steel slit damper with the inner section. Cyclic loading test was performed on the damper in order to investigate the performance of the self-centering box slit damper. The loading protocol was according to the FEMA 461 standard, which is specific for such testing. The test we can observe in this video. We can observe the vertical strips moving relative to each other. In compression of the disc springs, in the hysteresis, we can observe the flagship hysteresis loop of the damper. However, due to some limitation during manufacturing, there was a little bit of friction along this corner because of the external movement caused due to the symmetric welding. The overall behavior predicts the self-centering behavior of the damper. This figure shows the analytical model consists of the famous Bookman model for the slit damper combined with the multilinear elastic and multilinear plastic element to predict the behavior of the disc springs combined in parallel. Hook and gap elements are provided to control the stroke of the damper in compression and tension. The comparison shows the agreeable prediction if we neglect the friction forces of the outer and inner section. Further, to evaluate the enhancement in the seismic performance of an existing structure, a case study model of 6-story RC structure is chosen. Using the capacity spectrum method, it is retrofitted with the proposed self-centering box slit damper, and the similar structure is also retrofitted with the conventional slit damper. 7 non-linear ground motion are selected and scaled to the design basis earthquake DBE target spectra of Los Angeles, California to check its seismic performance. And then the results are compared, which are as follow. This slide shows the maximum interstory ratio of bare frame without any retrofit. This is with the retrofitting of self-centering box slit damper, and this is the retrofit with the conventional slit damper. As we can observe, both the conventional slit damper and the proposed damper have achieved the target performance of life safety. This slide shows the displacement time history of 4 ground motions. As we can observe, for the box slit damper, the residual deformation is least. Hence, we can observe the enhancement is the seismic behavior of the structure retrofitted with the self-centering box slit damper. When comparing the maximum roof displacement, the box slit damper is approximately 53% and 31% lesser compared to the conventional damper and the bare structure. However, as the post yield stiffness is higher for the box slit damper, the acceleration is a little bit higher compared to the conventional slit damper. Thank you so much for your attention. These are the references. For any other inquiries, please email me at these email addresses. Thank you for your attention.